Plotting here the epsilon for dynamical time, for free fall time, versus now the virial parameter, how gravitationally bound the objects are. These must be compilations of GNCs. The lines actually don't particularly go through the data. I mean, this is a polite way of saying do not fully capture. Sort of that just bad. There are other ideas about how. And maybe I can say that they're bad because to get low epsilon free fall, these turbulence models need to have pretty high virial parameters, high kinetic energy, quite unbound the systems, whereas the data don't indicate that. There are other models involving feedback, sweeping up material and colliding it to form structures. Feedback-driven models, I would say, generally have the problem. It's difficult to have them explain a steady-state star formation rate. They either tend to run away, or you'd have a big starburst, which would make other stars and other stars. It's not a way to make a stable star formation rate. There are other models linking to the galactic dynamics, Elmer and Silk, and then Mordecai. Many other groups have looked at this as well. What is the rate of forming the clouds out of the large-scale disk? The model I'd like to propose, and we've been working on for more than 20 years now, is actually giant molecular cloud collisions driven by galactic shear that can be the main trigger. During my thesis, this paper came out. This is not the famous figure from the paper of Kennicutt, but the next figure is what we call the dynamical Kennicutt-Schmidt relation. This is the surface density of star formation rate in a galactic disk, and then plotted against how much gas you have divided by this dynamical time. This is actually the orbital time at the outer radius of these disk averages. And this is a one-to-one line, which is basically saying that, in fact, 11% of the gas in a galactic disk system turns into stars per outer orbit. If you go into annually and do this locally, it's about 4% of the gas, total, atomic and molecular, turns into stars per orbit. So the model we've proposed involves shear-driven giant molecular cloud collisions. So it's the rate-limiting step for star formation is not the conversion of atomic gas into giant molecular clouds. There's already 50% of the ISM is in the giant molecular clouds. The rate-limiting step in this model is the creation of magnetically supercritical dense clumps, which are made in collisions driven by shear in this shearing disk. And a number of points to note about the collisional system. It's a two-dimensional system. The scale height of molecular gas is very similar to the size of GMCs. So collision rates are much larger. And it will depend on the rotation curve. So typically in a flat rotation curve regime, beta is the logarithmic gradient of the circular velocity versus radius. In a flat regime here, you'll have more shear than in the closer to the solid body regime. So in fact, Charles Gammie and Jerry Ostreicher and collaborators worked on what these collision rates should be with simple n-body simulations. And they found that the typical impact parameter is about 1.6 tidal radii from a cloud, which can be a few hundred parsecs for a typical GMC. So we put that, what's the collision time is the mean free path, what's the velocity at this impact parameter is the shear rate in the galaxy. You kind of put this into a Toomre Q of unity disk, and you end up getting that the collision time is about 20% of an orbit for every GMC in such a disk, modified by this beta factor. This is the prediction of the model. As you enter this solid body regime where beta rises to near unity, to first order in beta, you'd have this decrease. It's going as 0.7 here. And then if star formation is driven by collisions, then the star formation rate would then be this gas, how much gas you have divided by the typical collision time, and that's how you'd recover this sort of Silk-Elmer-Green dynamical Kennicutt-Schmidt law modified by this bit on beta. Okay, so that was what we put out in 2000. Roughly 9 years later, we put this into ENSO, AMR simulation, with PDR, heating and cooling, and actually that was done in 2018. So we have a population of GMCs orbiting in a disk, and we track the clouds and work out how often they collide. And the collision rates are plotted here. They are actually big clouds collide every 10% of an orbit, and the typical cloud may be roughly every 20%. So we would kind of verify the analytic prediction. Now, in the FANG's ALMA survey, big ALMA survey of nearby galaxies, they've trying to understand how does star formation vary with galactic environment. One of their main conclusions is that very little effect. But the main effect they do find, although they don't emphasize it very much, is that the shear time has the strongest correlation coefficient when they try and work out this is depletion time of their giant molecular clouds. The inverse of that is the star formation rate. One reason they dismiss this is because they think they think the lifetime of GMCs is actually quite short. So this is shown by this yellow band. Let's discuss that first. It's done by something called a tuning fork analysis, which is based on this cartoon. A cloud somehow forms. It has some lifetime. It forms stars. There's an overlap. Then the stars exist for a while, a few million years. And then by counting stars in different apertures, shown here, you center your aperture on a place of star formation or on a molecular gas feature, you can sort of build a model to constrain these various phases. What I've never particularly liked about this is it doesn't close the loop. Where does the cloud come from? If some of these results imply, the cloud lifetimes are only 3 or 4 million years, but in steady state, you'd have to reform the cloud from the H1 in such a short time. It seems very challenging. So with GenCoder, we've just put a simpler model where the clouds live forever. They form stars. The stars can drift away at some speed. And if the speed's of order 10 kilometers a second, you can get very similar estimates, very similar structure in these tuning forks. The time scale implied is basically the duty cycle of how often stars are forming. And then this 10, 20, 30 mega-year time scale could be actually the collision times. And then the other thing that they show here, their empirical collision times in this Sun paper are perhaps a factor of 3 too large, where they use the cloud physical size rather than the tidal radius. So that alone will correct this. So we're working with JWST now to make that correction. Anyway, the main thing is to look for this predicted dependence on the beta. So what's shown here is stuff we did with Adam Leroy about 10 years ago now, looking at early data and annually, what is epsilon orbit? All these dots here of different annually of these galaxies. And does epsilon orbit increase or decrease as we go from flat rotation curve regime, beta of 0, out to larger beta? Does this data decline? And we thought maybe it's declining, but the significance there is not so great. So in one of our summer student projects in 2023, Zaina, who was a first-year student, worked with JWST to analyze the FANG's data now and do this test to the best we can do it with the latest data. And never good to test your own theory, so I let them do all the numbers. We're just fitting to the bin, the medians here of the data. There's obviously a lot of scatter in the data. You can do various cuts. You don't want to work in the center of the galaxy because it's kind of messy there. But the number that comes out here is pretty close to 0.7, so we are encouraged. Anecdotally, there's lots of evidence for GMC collisions. There's even been a special issue in PASJ about various evidence in the galaxy for collisions. And let me just end here by saying, what are the implications here? If giant molecular cloud collisions are frequent, like every 10% or 20% of an orbit, or every 10 to 30 megayears, then, you can actually explain why roughly half of GMCs have retrograde rotation. That's observed in nearby galaxies and in our own galaxy. Whereas models of bringing all the GMCs to molecular gas from the H1 would be prograde. You can maintain turbulence in GMCs. This is a very natural way to do it. Extracts from galactic rotation. There are giant molecular filaments, which is studied here. There's a lot of great work that's been done here. Why they align with the galactic plane would naturally come out of a shear-driven model here. If you're measuring virial parameters, you would often get confused because sometimes you've got 2 clouds in there. So you'd overestimate the virial parameters when you have bound structures in there. The collision resets the clock. The GMC lifetime is reset after a major collision. And then, obviously, we are proposing it's how star formation is driven in these kind of galaxies. And circumnuclear disks as well. So I'll stop here. This is our team working on the project.
So I'll take the first question if I may. So this story, which is actually very convincing, does involve clouds of gas colliding with other gas. Most of those collisions are going to be supersonic, is that not true?
Yes.
Do you see evidence for shock-heated gas in all of these structures?
Well, that's a very good thing to mention. We have spent a lot of time, we have another group working on infrared dark clouds in our galaxy, looking for SIO, for example, the shock tracer, or looking for disturbed C+ kinematics around them. There are cases where we have seen that. Cosentino's papers, for example, have seen SIO in the Sarah 2010 around some very filamentary ITCs. But you have to be careful because it's the SIO signature, for example, would be relatively narrow features because you can also get SIO in protostellar outflows, which are broader. But you're absolutely right.
Any other questions? Tony?
So to what extent does this depend upon an underlying spiral potential in the stars?
It's independent of this. Everything I've shown you here in the simulation is there's no imposed large-scale spiral potential. Spiral arms would locally enhance collision rates, though. So that's the model can deal with spiral arms. What people have seen, in the FANGS data and other surveys, is that when a galaxy has a spiral arm present, it doesn't appear to enhance epsilon orbit. So it's not that spiral arms drive star formation more efficiently than without globally, like locally.
Okay, do we have another question here?
John, I have many questions, but I'll stick to one. So you kind of dismissed the Inuzuka feedback-driven model, and a lot of the observations recently, as you know, have been very supportive of that model. And you could reconcile these two things by saying that the expansion of these huge bubbles drives collisions, which I think is not in your model, but would get you possibly very similar answers.
Occasionally it could happen. I'm not sure which observations you refer to, but any feedback-driven model, I don't quite see how it can regulate. So it's...
The observations I'm referring to are things like the local bubble in 3D hitting the Perseus torus supershell.
Well, I'm sure it can happen occasionally, but I don't think it can be the major driver of all the star formation. It requires other star formation, because then it would sort of run away.
Okay, we'll talk later.
Yes, go ahead.
Great. I feel I need to defend turbulence.
Please.
And so this observations of viral parameter and efficiency is very tricky, right? Because we see gas instantaneously while star formation is necessarily average. And in simulation it can show, and if you do it properly, then you can explain the data. So this difference in trends is purely evolutionary.
Well, you're raising a point about the statistics of the dispersion in epsilon freefall, I think. Like when you look at clouds, there's quite a wide dispersion. Yeah, that can be explained with different evolutionary stages. Cloud collisions can naturally give you a reason why star formation is more clustered than the gas, and there's a large dispersion. Some clouds are not doing much, and others are doing a lot.
No, I mean more like this scaling of efficiency with viral parameter, right? The point is the star formation that we see now, it happened in conditions with different viral parameters sometime.
Okay, well, maybe you can.
Yeah.
I'm sure there are ways around. It's difficult.
No,
to...
it's the outcome of the model. Actually.
Okay.
So we have time for one more brief question.
Yeah. There's a team in Europe observed the cold gas in the early type galaxies, and they find the disk in early type galaxies. The project is called Wisdom.
Yes.
But they didn't find the star formation because the star formation was suppressed by the shear, and make the turbulence and the shear of the disk makes the cloud too fragmental. So, based on your picture, how to explain this phenomenon in early type galaxies?
Yeah, Wisdom. I was just in Oxford talking to Martin Euro about a month ago, and he didn't raise a problem particularly. Are the disks a few hundred parsecs in size? These are these ones right in some of these ellipticals, right? Well, I need to look at the rotation curve. You're raising a good point. We should test the model in more extreme cases, and right now our main test has been done in sort of the big normal disks that FANG's ALMA has looked at. So, Virgo. I mean, we looked at that. We looked from some of these systems. You're much further away, right? Typically 100 megaparsecs away, and it's tough to get resolve the data on good scales at these distances, but we can try.
I think to conclude, let's thank our speaker again. And the next speaker is Hector, Afonso, Cruz, Jeon. The first civilian here is in second. That makes it a expected model for the 21 billion signals, expedition 3 stars.
All right. So, hi everyone. My name is Hector. I'm a final year grad student at Johns Hopkins, and today I'm really excited to share with you some of our work on creating this purely analytical model to compute 21 centimeter fluctuations at cosmic dawn. Before I delve into the details of our work and our code, I'd like to first make my case for why we need a fast analytical model for. Oops, did that break? No, I think the connection. Okay. My laptop is frozen, unfortunately. So usually when this happens, I have to hard reboot my laptop. Is it possible for the next speaker to go? I'm very sorry.
Can you just, it doesn't do anything if you pull it out?
No, it's like, okay. Very sorry this happened. I'm so sorry.
Yes, hello. I'm a grad student from University of Texas at Austin, and today I'll be mostly talking about the work I did with my collaborators here, based on the paper that's on the archive since earlier this year. So the motivation for this work is the new JWST observations. So even before JWST, there have been observations of high redshift quasars that were very massive at early times. And JWST is only found even at those supermassive black holes at earlier times. So to form these systems, the standard scenario we think of a stellar remnant forming a black hole seed, and that black hole seed growing through accretion through some Eddington-limited rate, cannot produce these massive objects so early on, usually. So to produce these objects, we have to turn to more exotic scenarios, such as super Eddington accretion going above the Eddington limit, or maybe some more exotic massive seeds, such as the direct collapse black hole, or DCBH, which can form from gas clouds, massive gas clouds collapsing directly into a black hole seed instead of fragmented form stars. Another issue that arose with the JWST is this problem of overmassive systems. In the right plot, I show that the black hole mass to the stellar mass ratio of some of the observed JWST systems. And compared to the local ratio that has been calibrated quite well, many of these systems are overmassive or above the local relation. And then we have to understand how the coevolution between the supermassive black holes and the galaxies, we have to understand how these overmassive systems could have formed and will have evolved down to these local systems eventually with time. Of course, there are large uncertainties that I don't show here. There are uncertainties in JWST measurement of stellar mass and black hole mass. But for now, if we trust these measurements, there is some issue that we have to solve theoretically. Another issue or a development that came with JWST is that now we have observed a higher number of these AGNs at high redshift. We can do population statistic analysis of them. This is a black hole mass function from a paper that I worked with a postdoc at UT. So this is a black mass of redshift 3.5 to 6. So any scenario that is able to produce these extreme systems at high redshift should also be able to explain the population of early AGNs at earlier times as well. So to address this problem, for individual systems, I run a cosmological simulation. I specifically run the Gizmo code, and then a modified version which includes POP3 seeding and is calibrated to high redshift observations, so that we'll be better able to represent the high redshift environment. And for this work, we focus on the heavy direct collapse black hole seeds, as we believe that would be a better case or a more easier way to produce these overmassive systems and also these massive AGNs at early times. So for a few important details for our model, how we form our DCBH in our simulation, we have two criteria, the chemical and the density criteria. So the chemical criteria are written down there at the bottom. We have a molecular hydrogen limit, a metallicity limit, and a temperature limit. And all these chemical criteria are to ensure that the gas cloud does not cool efficiently down to low temperatures. This prevents the gas cloud from fragmenting. And then the gas can collapse isothermally into a black hole itself. And then we also have a density criteria so that the gas particle be dense enough for such a collapse to happen in the first place. So if a group of gas particles meets this chemical criteria, and if the densest gas particle among them meets the density criteria, we turn the densest gas particle into a sync black hole particle of a similar mass range, which is in the direct collapse black hole mass range about 10 to the 5 solar masses. And then after the DCBHs form, we grow them through the gas swallow model, and so such as a fiducial Bondi-Hole accretion model that's used in many simulations. And in this model, we have the black hole grow as long as there's enough gas particles swallowed nearby. So the equation for swallow probability is shown there. So if there's lots of gas particles nearby the black hole, it will accrete and swallow those gas particles and then grow massive. But if it doesn't, it'll swallow only a few gas particles and won't be able to grow as massive. And we have tuned this model so that the black hole will try to grow at the Eddington limit as long as there's enough gas particles nearby. So we can model the efficient accretion of these heavy seeds. We do this because in cosmological simulations, due to limits of sources resolution, we want to use the Bondi-Hole equation, generally due to some low resolution resolution of cosmological simulations compared to the actual physics of black hole accretion. These black holes don't generally stay dormant and don't grow at all. So this is a massive 10 to the 4 seed in a simulation using Bondi-Hole. And compared to the Eddington rate, these black holes stay dormant and probably doesn't realistically represent the actual physical mechanism of this black hole growth. Many GR-MHD simulations have shown that massive seeds could grow at Eddington. So in this gas swallow model, we try to capture that high accretion rate, but as the environment allows it, to see what the environment that can allow these black holes to form are like. So as a result, what we find is that generally the halo mass itself doesn't necessarily correlate with the black hole growth. So here's the two cases A and C that I show. And then case A generally has an order of magnitude higher halo mass than the halo gas mass compared to the black hole case C. But the black hole growth of case C is much higher or more efficient than the case A. So even though case A has a larger gas reservoir that's available in the dark matter halo, not all of that gas necessarily accretes down onto the black hole itself. So what affects the gas accretion more, we believe, is the local gas environment near the black hole. So this is around the 2 kiloparsec box around the black hole of the gas velocity distributions. And I show 4 cases here. Cases A and C from earlier, you see that the case A has a generally hotter gas particle that's streaming across the black hole particle at the center. Case B has generally a little bit colder gas particle that's circulating around the black hole. So this indicates that if a gas environment is denser on the black hole, the black hole will be able to swallow it more better and then be able to grow more efficiently. Cases B and C here, also case B showed higher growth than case D. In case B, you obviously see a group of cold gas particles nearby. Case D has generally very few gas particles nearby. So again, it's not just the overall gas available that's in the dark matter halo, but what the local gas environment around it as the black hole evolves that affects how these systems will be able to grow. So we then compare our results with observations. Here are some quasar and JWST observations compared to the simulation results in the solid lines, and some local M-signal relations in the dashed lines at the bottom. And we see that we're able to produce these massive JWST systems and these overmassive systems as well on the right with this heavy seed and efficient accretion model. But maybe not the most extreme quasars at high redshift. Maybe we need super Eddington accretion for that, which we don't really have in our simulations right now. And even though we do produce these overmassive systems, they don't evolve down to these more local relations by the end of the simulation. We believe that's a limitation of our box size because we have a zoom-in simulation. We have a small box size compared to the whole cosmological environment, and we don't have the larger density modes that will contribute to structure formation at lower and lower redshifts. So maybe not enough stars form in our simulations by the end or redshift 5 or so that these systems don't generally evolve down to these more local relations. In case D here, you see like a merger case where the relation is brought down by a lot. So maybe in a larger box where more gases are able to form, such events will be more common so that these systems eventually evolve to these local relations as time goes on. Now that we have these extreme cases, we also want to address the whole population statistics of AGNs at high redshift. But to do that in simulations is difficult because we need a large volume, high resolution simulation. And then because we also want to test different scenarios, we'll have to run multiple of these very computationally expensive simulations. So instead, what we try to do is use a semi-analytical model. So we specifically use the A-sloth code, which is a semi-analytical code that includes path 3 for star formation, feedback, and is calibrated against high redshift observations. And then we use the extended trajectory tree analytical merger tree instead of a dark halo simulation tree, because it'll be faster and quicker to run these, and then it'll be easier to test multiple mod scenarios of black hole formation and evolution using this analytical merger tree. And because A-sloth didn't originally have a black hole model, so I've built black hole seeding and accretion, merger, and feedback models of like both light seeds and heavy seeds, so to test under what conditions and under what relationship between the stars these black holes might evolve and the overall like volume of the universe. So this is still a work in progress. So what we have are just preliminary results so far. But what we first find is that very different scenarios right now can reproduce observed growth. So here are just 3 scenarios: heavy seeds, nth-limited, and superheterodyne growth. All 3 scenarios can fit the observations pretty well. So to distinguish between these scenarios, we have to go to higher redshift, or redshift 10 or 9, which, as an example, we show here. And here we can definitely see some differences between the scenarios. But at later times, as the observation limits currently allow, we cannot. So we believe higher redshift and maybe lower mass observations are needed to fully constrain how the full population of AGNs and supermassive black holes can be formed in the early universe. Yeah, and then I'll just leave on my conclusion slide here. Thank you.
Yes, I'm struck by you're referring to observed black holes. So what does JWST actually observe and see that you interpret as black holes?
So these mass functions are from like broad line spectra. So if I believe if galaxy spectra shows like a broad line, and in the case of presence of an AGN outflow, which I believe the paper tests to see if it's robust, and if it is, it identifies an AGN.
It's an AGN-like object.
Yes, I guess that's almost most of the AGNs at high redshift, because you can't do reverberation mapping or something like that at higher redshifts.
Any other questions? Sorry, go ahead.
Yeah, very nice work. How common are your direct flux black holes in your models here? I know you've got zoom ins, but can you say something about the global co-moving number density?
I think around like 10 or so form in my box, but I believe that's too many for now, because we have like a simple CD model. That's why I also wanted to move up to like the semi-analytical model for now, to have more accurate seeding channels. Yeah.
And how big is your box?
Box like a few megaparsecs, so I think too large. Yeah.
Okay. Any questions? So let's thank our speaker again. Got a word this time?
Hi again.
So just get started when you're ready.
First of all, I'm deeply sorry that happened. I think it's time for a new laptop.
Okay, since I'm the person in charge here, we forgive you.
Thank you very much. Okay, so yes, final year grad student at Hopkins, working with Julian Munoz and Mark Kamienkowski, and today I'm really excited to share with you our fully analytical model for 21 centimeter fluctuations. Now, before I go into the details of our code, I'd first like to make our case for why we need a fast analytical model for 21 cm fluctuations. And the best way, I think, to make this case is to compare current modeling techniques to those in an already well-developed field, the CMB. So the CMB already benefits from a robust theoretical framework informed by decades of observations at this point to compute the signal in the first 380,000 years of the universe. And while you do have some scary set of equations of motion to compute early background and metric perturbations, you're able to plug these into these black box codes that we call Boltzmann solvers, like Camber class, that evolves these perturbations over time, and out pops out nice clean power spectra that tells us the spatial distribution of CMB fluctuations. I'm afraid we don't have that luxury in 21 cm cosmology, because we have nearly the exact opposite problem. We use a highly uncertain theory that suffers from a dearth of observations at such high redshifts, And we attempt to compute the signal spanning the first billion years of the universe, dependent on the first luminous sources that heat and ionize the IgM, which live in dark matter halos sourced by cosmological initial conditions. So the cumulative impact of cosmology, astrophysics, and randomization is encapsulated in this one equation for the 21 cm brightness temperature. So all would have been well if T21 was restricted to the first and last terms, which are relatively easy to compute with current methods. We have decent Boltzmann solvers to compute cosmology, and we can nail down the neutral fraction with HIREC and other codes. It's really the middle astrophysics terms that gives us a headache, specifically the Lyman alpha background, which couples to the IgM and brings forth an absorption feature, and X-rays, which heat and ionize it. And it's hard for three main reasons. Since stars produce the photons that impact the IgM, we can describe the Lyman alpha and X-ray backgrounds as the integrated impact of the star formation that produces these photons, star formation rate density, SFRD, integrated over photon paths traveled. So we're left to model a non-local integrated effect of the uncertain spectroscopic signatures of early stars and their dependence on local cosmology through local density and velocity fields. And I'll go through each of these in a bit more detail. So what do I mean by uncertain astrophysics? The earliest epochs of the universe give rise to the first generations of stars, population 3 stars, which we think are astrophysically distinct from POP2 present-day counterparts. We assume that they're twice as efficient at producing UV photons per baryon and up to 10 times as efficient at producing ionizing photons per baryon. These numbers you can get from some stellar population synthesis code like BPAS. And most importantly, we assume that the earliest stars form in the earliest dark matter halos, which were much lower in mass and therefore more susceptible to different types of feedback than the ones that we see at the present day. Of these feedback effects, the most important is that from the relative velocity field between cold dark matter and baryons. These are sourced from baryon acoustic oscillations in the pre-CMB universe. At kinematic decoupling around a redshift of 1060, these BAOs freeze out, leaving baryons with some supersonic relative velocity to that of dark matter. And this supersonic relative velocity inhibits star formation in several ways. The most prominent impact, though, is that it makes it harder for early halos to accrete cold baryons from the IgM to form stars. So baryons with high velocities struggle to fall into the potential wells of early low-mass halos, effectively quenching them. To compound the problem, the integrated effect of radiative fields is annoying to compute because it's a non-local effect. To compute the UV or X-ray specific intensity at any one location in space, one must integrate over all the stars surrounding it that emit photons that travel to that location. And we know that photons travel long distances. From the recent XQR30 spectroscopic survey of very bright quasars, using the Very Large Telescope, we know that UV photons travel on the order of megaparsecs, X-rays travel on the order of hundreds of megaparsecs. So in essence, the astrophysics at any one location is dependent on the astrophysics of its surrounding, all sourced by cosmological initial conditions. So we've established that the evolution of T21 is messy compared to the cosmology-only CMB, but that doesn't stop us from trying to make meaningful studies of the early universe. So how do we solve these problems, and how do we connect theory behind the high redshift Astro and Cosmo to the impending data releases from telescopes like Hera and the Square Kilometre Array? The most popular answer is to simulate it. There's two flavors of these simulations, these radiation hydrodynamic simulations like THESN and Cosmic Dawn 3, and semi-numerical recipes like 21 cm fast. The former of which performs radiative transfer on from sources on the IgM, and the latter evolves halos on some grid. Both methods tend to be quite computationally intensive. RHD sims take anywhere from weeks to months to run on a cluster, and semi-numerical codes still take hours. And both tend to probe small volumes, are inflexible to probing beyond lambda CDM concordance model physics. So as an alternative, we present our fully analytical code, Zeus21 version 2, which doesn't need a grid of voxels to simulate early galaxies. And our main update is to include the effects of POP3 stars into the mix and the various feedback processes that hamper their formation and govern their evolution from cosmic dawn all the way up to the beginning of ionization. So to generate power spectra, we take a step back and see how fluctuations in T21 are related to fluctuations in the star formation rate density. So on the leftmost plot, I show the SFRD in units of solar masses per year per cubic megaparsec over fractional matter density delta. And intuitively, the curve shows us what we expect. Regions of the universe with higher density give us higher star formation, more density, more baryons, more stars. But just looking at the plot by eye, it looks fairly log linear. I also plot an analogous plot on the right, SFRD versus relative velocities, and it also shows us what we expect. Regions of the universe with higher relative velocities cause less star formation. And just by eye, the curve looks like exponential decay. We then fit the slopes of these curves on the fly. So the density plot has a slope encoded in some effective bias gamma, and the velocity plot has a curvature encoded in its effective velocity bias mu, which means that we can claim any realistic realization of the SFRD could be described as a separable product of the average SFRD at any given redshift times these factors exponential in density and velocity. So what's the point of all of these approximations? Back to our treatment of T21, we claimed that the UV and X-ray backgrounds are integrals over the stars that produce them. From our fits, we can approximate this as some sum in our separable exponentials in density and velocity, which means that we can describe correlations in T21 in terms of correlations of e to the delta and e to the minus v squared in a way that doesn't need simulations. And the main benefit is that instead of running a full 6-hour, 1.5 gigaparsec simulation on a cluster, our code takes 3 to 5 seconds on a laptop. So in 3 to 5 seconds, I can generate power spectra like this. At a redshift of 16, here I plot the reduced power spectrum over wave number. It's a measure of variance across scale. And we expect in a homogeneous isotropic universe that things vary less at large scales and more at small scales. As we see, compared to the POP2 only case in white, POP3 stars generates radiative fields earlier, so photons travel comparatively farther, and you get more power on large scales. At adding VCB feedback yields our fiducial curve in red. And when compared to simulations, our treatment of 21 cm fluctuations at cosmic dawn is very precise. Here I show in solid colors the Zeus power spectrum at redshifts 13, 16, and 19, offset by factors of 10 for visualization purposes, compared to the dotted power spectra from 21 cm fast simulations. And across all of them, I get power spectra that are 7% precise across the majority of scale, which is still remarkably within the 20% theory error that we ascribe to all 21 cm studies. As we get more data, I'm sure we can better inform our models to mitigate these differences. The last thing that I'd like to remark about is a geometric feature of our power spectra, specifically these bumps. So why do they matter, right? They're sourced by BAOs, but they're not BAOs. They come from the spatial modulation of the SFRD due to velocity fluctuations and not baryons. But while BAOs fluctuate on the order of 5 to 10%, velocities fluctuate on the order of unity. At kinematic decoupling, the average is around 26 plus or minus 29 kilometers per second. So velocities are much more important at determining where star formation occurs than matter over densities at high redshifts. But because these velocities are sourced by BAOs, their spatial distribution also should express the same statistics, which means the position of these peaks actually measures the Hubble parameter times the sound horizon. So VAOs present us a new standard ruler for measuring cosmic expansion and geometry at cosmic dawn, well into the matter-dominated epoch. So here I show a plot of the Hubble parameter divided by h of z if the universe was just purely matter. And it'll be interesting in the coming years to compare our VAO numbers and how they stack up against the ultra-precise CMB and large-scale structure, and also the other late-time TRGB and supernovae constraints. And it's available now. So we also had other goals in mind when building Zeus. We wanted to make a legible code with a low learning curve so that beginning scientists and undergrad cosmology classes can easily pip install our code and start playing with power spectra to learn cool stuff about cosmic dawn and reionization. And we hope that with our code, we can both bring rapid precision to cosmic dawn and give beginning scientists a powerful tool by bringing about the first billion years in seconds. Thanks, everyone.
This is where I envy Avi who's not here, because Avi would have lots of questions. But I do have one question. Do heavy elements play any role in this discussion? Because I thought one of the jobs of the first generation population 3 stars is to start producing heavy elements.
Yes. We don't have any assumptions about metallicity and how they impact the number of ionizing photons per baryon, or anything else about POP3 spectroscopic signatures. I believe in a future update, which will hopefully come in the next 5 to 6 months, we'll introduce a bit more of a flexible parameterization of what happens if you start tracking metallicities for POP3 stars, what happens if you play with their initial mass functions, how that contributes to the UV and X-ray outputs. So that's something that's in process.
Okay, thank you. Any other questions? Yeah, go ahead.
That was a great talk. So what sorts of angular scales do you need to access for VAOs at, say, redshift 13, or alternatively frequency scales in the line of sight direction?
I am not sure what that translates to, but we base our models off of what Hera can see, and it's most able to probe wave numbers from 10 to the negative 2 to 10 to the 0 inverse megaparsecs at redshift 13.
But if Hera could perfectly remove foregrounds, they would be able to see these scales.
If Hera is perfectly able to remove foregrounds, yes, they will be able to perfectly see these. Given a pessimistic foreground assumption, I believe you'd have to push VAO observability up to like redshifts 16, 17, 18 and higher. But we'd have to see how one deals with systematics to be able to get to that high.
Do you have any other questions? Thank you again. Who was doing this one?
Yeah.
Tony, sorry.
Oh, so is there any possibility of seeing these at lower redshifts where we can actually see galaxies?
So in terms of the 21 cm signal, not enough because most of it's ionized. In terms of the matter fluctuations, I believe there was a paper in 2013 about how relative velocities cause some fancy matter affection that can distort what PFK would look like. Not enough sensitivity by current ground-based telescopes to be able to detect a signal, though.
Yeah, but LSST is coming, and
LSST.
Euclid.
Yeah, I think Roman Euclid might be able to. I'm not quite positive on that, but I hope they will.
Is the, excuse me, VAO's redshift must be dependent on at what Z's the first top 3 stars formed?
Can you repeat that? I'm sorry, I didn't catch that.
What is the dependence on when top 3 stars formed for the onset of VAOs?
So the fortunate thing is that the position of the peaks of VAOs are astrophysics independent. So it doesn't matter on the timing of when top 3 stars form because the acoustic scales are already frozen in well at kinematic decoupling. So we can, the nice thing is it's astrophysics flexible. There's no dependence on star formation history.
Let's thank our speaker again. Okay, then our fourth and final speaker is Panamarev from Oxford. Case for an intermediate mass black hole in the Galactic Center. Insights from in-body simulations.
Thank you. It's my pleasure to be here, and I'm a postdoc at the University of Oxford. I'm also affiliated with Fesenkov Astrophysical Institute in Kazakhstan, and today I'm going to talk about possible presence of an intermediate mass black hole in the galactic center. Let me start with a brief overview of the Milky Way nuclear star cluster. So this is a schematic image of Milky Way nuclear star cluster. We know that it has a supermassive black hole in the center. It has a population of stars surrounding it. Like in the red, you see these are the population of old stars. So they're roughly spherically symmetrically distributed. And also, you see this, it has the stars in blue, which are very young stars, and they appear to be arranged in one plane, or very close to one orbital plane. So this is so-called disk of young massive stars. And in this talk, I will focus on the dynamics of these stars, of these very young and massive stars. There are several open questions about the disk of young stars. Like one of them is how all the stars formed. Another question is why are they arranged in one plane, basically in a stellar disk? Another question is which dynamical processes drive the evolution of this system? And final question, which I will focus on today, is there an intermediate mass black hole somewhere within the stars in the disk? So if we look closer into the stars of the disk, so this picture shows a distribution of angular momentum vectors of these young stars. And you can see it's actually not just one disk of stars, but at least there is another structure. So there is a second stellar disk, which has orbital angular momentum vectors in opposite direction compared to the main disk. And there is another work, and so this is shown by the Galactic Center group at UCLA. And there is another work led by German group. They show that there are even more structures in this disk. So they claim that there are at least 5 different substructures. So, and another interesting thing is that if you slice the distribution of stars into bins according to distance from the galactic center, you will see that this substructure, they depend on the distance from the supermassive black hole. So, but all the stars, they appear to have the same age. So probably they formed in one star formation episode. And so the question is how these stars could form. And we propose a scenario that they formed from a gaseous accretion disk. Like if our galaxy was active in the past, the interaction of stars with the gaseous accretion disk could lead to formation of stellar disk. And at the same time, the accretion disk can become unstable and form stars on its own. But in this case, you expect a thin stellar disk on nearly circular orbit. So you expect just one disk of stars. And the question is, why do they see all these different substructures? And the idea is that probably there is an intermediate mass black hole somewhere within the disk, such that it can disrupt the disk to form these different substructures. So to check this, we run direct and-body simulations. So what we do, we have central supermassive black hole, we have a disk of stars in yellow, we have an intermediate mass black hole, and also we have the old star cluster shown in blue here. And we run multiple simulations, and this is for the innermost part of the galactic center. This is the central half of the parsec. And so we change parameters for the intermediate mass black hole, and we tune everything to the Milky Way supermassive black hole and Milky Way nuclear star cluster. And this is direct and body code just by solving equation of motion. And we do this, we run this code on a GPU cluster. This is a highly parallel code. We have a small cluster which we manage ourselves, and we run all the simulations on this cluster. Okay, let me show you results. Turns out there are 3 different regimes depending on the mass ratio of the intermediate mass black hole and the disk of stars. And turns out that the most interesting regime is when mass of intermediate mass black hole is comparable to the mass of the disk. And in particular, this model, which shows here for the intermediate mass black hole, so if it has these parameters, the most importantly, it should be retrograde with respect to the stellar disk and moderate eccentricity. You can actually split the initial stellar disk into multiple substructures. So here you can see angular momentum vectors of all the stars. So we have central supermassive black hole. The yellow is the stellar disk, red is the old star cluster, and this spot is an intermediate mass black hole. Now we start the simulation, and you can see how intermediate mass black hole can twist and disrupt this stellar disk. And also note that it happens on this time scale, so of few mega years. So exactly corresponding to the age of these stars. So in the end, after 7 mega years of evolution, you have several different substructures. And actually, you can see that some of the substructures have opposite angular momentum vectors. Basically, opposite angular momentum vectors have opposite directions. Now, this is exactly the same movie from exactly the same simulation, but now on the projection to the sky. And here the color coding shows the distances from the supermassive black hole in log scale. And you can see how all these substructures are being formed again. And so yes, here is this IMBH. And you can see that in about 5 mega years, you already have 4 different substructures. So this was the initial condition. So the outermost structure, it resembles the initial condition. Then you have this green, and then you have 2 innermost structures. So we can compare it with the observed distribution if we rotate our system such that the initial condition would be here. So this is corresponding to one of the observed outer structures in the disk. And you can see that you can roughly recover all these substructures, at least qualitatively. You can form these different substructures. Now, let me briefly describe analytical model, why this works and what we can expect. So you can understand this if you imagine a very simple picture. So imagine you have just 4 bodies. You have central supermassive black hole, and this is, by the way, again, in the angular momentum space. So you have a supermassive black hole in the center, then you have an intermediate mass black hole in the equatorial plane, so its angular momentum vector will be exactly at the north pole. And then instead of stellar disk, let's just imagine we have 2 stars, which have very small relative inclination angle. And so we can study how IMBH drives the evolution of these stars in a smooth background potential. So in this case, if we have a star moving in a smooth background potential due to the mass, due to the enclosed mass, it will trace ellipses which will be precessing. So after on the time scales much longer than 1 orbital time, but much shorter than the 2-body relaxation time of the system, you can approximate orbit of 1 star as a Keplerian annulus. So it will be an annulus with inner and outer distances corresponding to pericenter and apocenter of the star. So what eventually will happen if you have just 2 stars moving in this potential, you can imagine the stars as 2 Keplerian rings. Oops, sorry. You can imagine the stars as just 2 Keplerian rings interacting with each other. And in this case, you can derive the equation of motion. And it turns out that the angular momentum vectors of the stars are driven by the torques between these rings. And you can see that actually it shows that these rings will just precess about the angular momentum vector, so about the total angular momentum vector, where this omega will be the precession frequency, and L is just the initial angular momentum vector. And if you have basically 4 systems with 4 bodies with basically it will represent 3 different rings, intermediate mass black hole and 2 stars. I'm about to stop. So you can understand how the IMBH can torque the stars basically, and how can it disrupt this initially coupled, initially precessing system. And so what you need to do is you need to just compare the Muschel torque with the difference between the torque of IMBH to one component with respect to the second component. And you just need to derive analytical expressions for these precession frequencies, which you can do in all the cases, and you can fully understand this problem. And now to understand what happens with the disk, you just replace these 2 stars by a stellar disk. And in the end, you will need to derive analytical expressions basically for the precession frequencies due to the disk, and then compare what happens, and then compare how basically IMBH torques the disk versus how it torques some of the stars within the disk. And this model predicts exactly the same, that you need a retrograde IMBH with moderate eccentricity to disrupt this disk into multiple substructures. So you will get something like this. If you start with nice disk, you will split it into these substructures. Okay, so in the end, if we ask a question, if there is an IMBH in the galactic center within the stellar disk, then we can say, yes, if disk formed in one star formation episode, if the ground halo is isotropic, and IMBH should have the comparable mass with the disk and be initially on retrograde orbit. So I'm going to stop here, and yeah, thank you very much. So I'm visiting for today and tomorrow, and I'm located exactly below this auditorium in D16. Please reach out if you have more questions.
But just to be clear, one IMBH can produce structure that resembles what's seen in the distribution of angular momentum in the vicinity Sagittarius system. Is that what you're saying?
So I'm saying you need one intermediate mass black hole of the mass comparable to the stellar disk on retrograde orbit with respect to the stellar disk, and it can disrupt the disk into these substructures which we see.
Thank you.
Thanks for the nice talk. What is the time scale for the intermediate mass black hole to settle very close to Sagittarius star, where I understand there are limits on the presence of such a black hole?
Yes, sure. It depends on how you form the IMBH, how it comes, right? So if it comes from globular clusters, let's say, the time scale can be long. But what we do, we assume that IMBH was already there when the disk formed. And you can also form IMBH in situ by just colliding the stars. So there was a paper by Senai Rosa and Smadar. They showed that you can form IMBH exactly in the galactic center, basically. And yeah, so our assumption is that IMBH was already there when we had this accretion disk, and when the stellar disk formed, IMBH was somewhere in the disk, but in different plane.
But I'm asking, how long does it take to just to settle into the center?
It depends on the mass of the IMBH. Like if you're considering IMBH of 10 to the 3 solar masses, it takes hundreds of years.
I was wondering, can you scale this problem up to the entire galaxy with the interesting constraints on the presence of one ray supermassive black holes in the galaxy?
This will be a bit more difficult because in our analytical model, we assume that we have these Keplerian rings. So you need to, so the time scale, assumption of time scales is that you wait much longer than the orbital period, such that you have these precession periods. But on the galactic scales, I think we don't have we don't wait for so long. We don't have so many orbital periods to exactly to rescale our analytical model.
Yeah, thanks for the talk. Would you said 10 to the 5-ish black hole in the nuclear region affect the flux that you'd expect of Hill's mechanism runaway stars that are thought to come from Sagittarius star in a meaningful way?
Yeah, so IMBH can affect the Hill's mechanism. So basically, it can repopulate the lost columns, and also it can form. Basically, the stars can approach the IMBH very close, and you can form high velocity stars this way. So without Hill's mechanism, just by encounters with the IMBH, you can form high velocity stars as well.
Okay, well look, let's thank all of our speakers.
What does a thing like that do to the gas?